So in this video we're going to go over some important notational considerations that we need in our pocket before we continue. I probably should have introduced this sooner, but I'm going to introduce it now. And we're going to introduce it in the context of something we already know how to do. So I'm going to walk through this the way that we've been doing it, and then I'm going to show that there's a different way to do it. And the different way of doing it becomes necessary when we're integrating and I can't find a closed form answer. So here's a simple separation of variable problem. It's a dy dx equals xy. And we already know how to do this. We separate variables. 1 over y dy equals x dx, and then what we've been doing, and we're going to show that we can do it differently. What we've been doing is integrating both sides, and then recognizing we get a constant of integration on each side, and we combine that constant into a single constant of integration, and then we slide through the solution process. We get the natural log of the absolute value of y equaling 1/2 x squared plus a constant of integration, and then we exponentiate each side base e, so we wind up with y equals e to the 1/2 x squared plus c, and then we recognize using exponent rules we can rewrite this as e to the c times e to the 1/2 x squared, and then we recognize that e to the c is just a third constant, and so instead of subscripting it with a 3, saying we've now got two constants that we combined into a guy here, say hey, we just keep using c for our constant, so we get ce to the 1/2 x squared. And then we solve for c using our initial conditions. When x is 0, y is equal to 2. So we plug in the 2. We get c e to the 0 squared times 1/2 is all going to be 0. And then we recognize that e to the 0 is just 1. So we get 2 equals the constant. And then we update our model with the constant. So we get 2e to the 1/2 x squared. And that's how we've been doing it. So what we want to recognize is we can do this a little bit differently. When we get to this step right here where we're ready to integrate, we can do this differently than how we've been doing, and updates available. That's exciting news for everyone. So let's say I introduce a variable t sub 1, and t sub 1 runs from the start x value, which is at 0, and it runs up to some x, and then t sub 2 starts at the y value and it runs out to wherever y runs. Y is going someplace. So we could change the notation here. I could say, hey, this is the antiderivative of 1 over, here's my t sub 2 variable, and then it would be dt sub 2. So it's the same integral, just introducing a different variable, equaling, and I'm going to integrate, and this is going to be, instead of x, I'm going to call it t sub 1, dt sub 1. And now you run over your interval. It started at 0 and it went to x, and this one started at 2 and it went to y. And then we can continue from here. I can integrate, so I get the natural log of the absolute value of t sub 2 running from 2 to y, equaling, here I get 1/2 t sub 1 squared running from 0 to x. And then we do what we usually do when we integrate. We plug in the limits of integration. That's an ugly 2. Let's fix it. So we would get the natural log. We'd replace t sub 2 with the y, minus, and then replace the t sub 2 with the 2. And this equals, we'd get 1/2 x squared minus 1/2 0 squared. So we wind up with the natural log of y equaling, we get 1/2 x squared, and I can add the natural log of 2 to both sides. And then I can exponentiate base e just like I did previously, so I get y equals e to the 1/2 x squared plus the natural log of 2. And then we can use exponent rules to break this e to the natural log of 2 times e to the 1/2 x squared. But e to the natural log of 2 is just 2, and we wind up with y equals 2e to the 1/2 x squared. So we wind up with the same solution by changing our indefinite integrals here, which required that we get the constant of integration, to definite integrals by renaming the variables. So the other thing that we can recognize here is that we might not be given an initial condition. Maybe we don't know what the initial value for x and y are, and we just represent them with x naught, y naught. So all that would change over here notationally is I would run this interval from x naught to x. If x is 0, then it plays out the same way that it did. If x naught is something other than 0, then it'll play out differently. And here's the y naught. And then on the integrals, the lower bound of integration would be the y naught, where we're starting if we don't know where it is. And the lower bound of integration would be the x naught. And usually x naught is going to be 0, but it doesn't have to be 0. And then that would run this from y naught to y, and this would run from x naught to x. And then over here, instead of having a 2, we would just have y naught sitting in here. And instead of 0 squared, we would have x naught squared. And if x naught happens to equal 0, then it cleans up the way that it has been. So the only thing that changes then is we have a y naught here instead of a 2. And it's still going to have the minus 1/2 x naught squared. And then we're going to exponentiate base e, so this is going to add on the 1/2 x squared term, x naught squared, sorry, 1/2 x naught squared is going to be part of the exponent now when we exponentiate each side. Instead of a 2, this will have the y naught in it. And then when we break this up, we're going to wind up with, we're still going to be able to break it into 3 pieces using the exponent rules, but we'll have an e to the negative 1/2 x naught squared, and then times the e to the 1/2 x squared that we've been getting. And so when we, and then with this cleans up in the next step, we get e to the natural log of the y naught sitting in here. So we still wind up with the y naught, and in our original case it was a 2. The y naught was equal to 2. So whatever y naught is going to wind up here. We get e to the negative 1/2 x naught squared times e to the 1/2 x squared as our particular solution if we start with x naught, y naught as our initial conditions. And the idea is if x is equal to 0, then we get e to the 0 is 1. We get y naught times 1 times e to the 1/2 x squared. We wind up with just knowing that we need to put whatever y naught is in there if x naught's equal to 0. So it's an alternate way to do it, but it's important because if we have an integral, for example, the integral of e to the t squared dt, it's a very simple looking integral, but it doesn't have a closed form solution. It doesn't have an algebraic solution. In other words, we can't integrate this. This is an integral that has to be approximated using approximation techniques. So what we do then is we let t run from some beginning value x naught out to some ending end value x, and then we put that limit of integration from x naught to x in here. And if we have an integral for which we don't have a closed form integration, then we need to do it this way. If we know what the initial x is, it's going to be the lower bound of integration, and we're going to integrate from x naught to x. So this form is the form that has to be used when we have an integral that we can't evaluate into a closed form. It doesn't integrate nicely, and unfortunately most integrals that exist in the universe would be integrals that you wouldn't be able to integrate nicely, and you would need to approximate them.